In this video, we're going to look at an ICE table or an equilibrium system. But in this case, we're going to have initial concentration of chemicals, but we're not told the equilibrium concentration of any of the chemicals. So we don't have an easy way to populate our ICE table where we can just find the change and then apply that to all the chemicals. Instead, we're going to be told the initial conditions of some chemicals and the equilibrium constant, or the Kc. Now, this question that we're going to look at is going to use the Kc like we've used before. It's going to use an ICE table, but we're going to go a different direction with it because this Kc that's provided for us in the question is going to be necessary to figure out how to calculate the equilibrium concentration for all the chemicals. We'll do the question in a second, but I want you to understand that the initial setup, so the initial concentration of the chemicals and the Kc are the only things that I've been provided here, and that without using a graphing calculator and the quadratic equation, so if we can't graph this information, then we are limited in the kind of questions I can ask. So I'm going to ask questions, I'm going to solve them not using the quadratic equation, not using your graphing calculator because that's not required for Chem 30. If you can do it with your graphing calculator and you can show me how you were supposed to have calculated that, I'm okay with it. You'll get the right answer, but it's not actually a requirement of this course. So in this question, it says in a 500 milliliter stainless steel reaction vessel. So that's half a liter, first of all. So that's 0.500 liters. Carbon monoxide and water vapor react to produce carbon dioxide and hydrogen. They tell us the temperature, but again, that's because Kc, or the equilibrium constant, is specific to a temperature. Evidence indicates that this reaction establishes an equilibrium with only partial conversion of reactants to products, so it's at equilibrium. Initially, 2 mole of each reactant is placed in the vessel. So to get their concentration, I'm going to take 2.00 mole, and it's going to be divided by 0.500 liters, and this is going to be 4.00 mole per liter. And that's my initial concentration of both of the reactants. So I'll put that into my table now, and that my other chemicals, the products, are not actually present at the beginning. So it says what amount concentration, so chemical amount concentration, mole per liter, of each substance will be present at equilibrium. It tells us that the Kc for this reaction is 4.200 at the 900 degrees Celsius. So right now, I don't have any equilibrium concentrations, so I can't fill in the table. But they did tell me that the Kc is 4.20. The equilibrium constant is going to be equal to the concentration of the products, so carbon dioxide, raised to the power of 1, because that's its coefficient, times the concentration of hydrogen gas, which is the other product, raised to the power of 1, because that's its coefficient, divided by the reactants, so carbon monoxide gas, raised to the power of 1, because that's its concentration, and water vapor, raised to the power of 1, because the coefficient for the balanced reactions, they're all 1. So this is my Kc expression, and I have the value. Now, at this point, I don't really have an obvious direction to go, but let's say that we made carbon dioxide, and we made X amount of carbon dioxide. That means that you're increasing the concentration of carbon dioxide from 0 to X, so it changes by plus X. So you're going to get plus X times 1 over 1, because that's the coefficients. So I will also get plus X hydrogen. So I'm going to have X amount of product being made, and I'm going to use up X, and since it's a 1-to-1 ratio, we're going to subtract X. So 4.00 minus X is the amount of carbon monoxide that should be left at the end of this. This will also be minus X times 1 over 1. So minus X, this is 4.00 minus X. And now by applying these values to my Kc expression, I know that my Kc, which is 4.20, that was what was given to me, is equal to X times X, because that's these two values, divided by 4.00 minus x times 4.00 minus x. So I've used these two values. And so 4.20 equals x squared over 4.00 minus x squared. So now to solve this, I'm going to take the square root of 4.20, which is 2.05 equals x, so I'm going to take the square root of this, and the square root of this. So the square root of 4.20 is 2.05. The square root of x squared is x. And the square root of 4.00 minus x squared is 4.00 minus x. Now I'm going to try to solve for x. So I'm going to take this, and I need to get it out of the denominator. So I'm going to multiply this side by 4.00 minus x. That's going to cancel these out, and I'm going to multiply this by 4.00 minus x. So I'm going to get 8.20, that's this times this, minus 2.05x. So that's x minus x times 2.05 equals, now I've canceled out the 4.00 minus x in the right-hand side of this equation, and it leaves me with just x. So 8.20 minus 2.05x equals x. I'm going to group my x's. So I'm going to take this over to the other side, and I get 8.20 equals 3.05x, right? Because I'm going to add 2.05x to both sides of the equation. And so I can now solve for x. 8.20 divided by 3.05 equals x. So I get 2.6885245 9, I'm going to go with 2.69 is going to be my value, and that is my value for x. So this is 2.69, this is 2.69, and this is 4.00 minus 2.69. So this is going to equal 1.31, and this will be 1.31. And that's how we can calculate the equilibrium concentration for all of the chemicals. I'm going to assign an amount of this being made as a variable. I'm going to use my my change step and the stoic ratio, and then I'm going to do some rearrangement of this equation to sort it out. So this strategy works if I've been given an equilibrium constant and an initial concentration. I will try to stick with questions where this is possible to do without the quadratic equation. If you had gotten to this point here, you could have used the quadratic equation to sort this out directly to find what x is, and then apply x to each of the sections here.